Welcome! In this session, we'll tackle the problem number 968, binary tree cameras. This is a fascinating challenge that involves optimizing the placement of cameras in a binary tree to monitor all its nodes. We'll explore different approaches, analyze their complexities, and break the problem down step by step. Let's dive in. In this problem, we're working with a binary tree, and our goal is to monitor all its nodes using the minimum number of cameras. Each camera installed at any node can monitor not only that specific node but also its parent and immediate child nodes. This means the placement of each camera determines the coverage for multiple parts of the tree. The input to the problem is the root of the binary tree, where each node is represented by a tree node object. This object contains the value of the node, though its value is irrelevant for solving the problem, and references to its left and right child nodes. Our task is to return an integer that represents the minimum number of cameras needed to ensure the entire tree is covered. To understand the problem more concretely, let's look at our first example. Here, the input tree is represented as 0, 0, null, 0, 0, and the structure of the tree is shown visually. We have a root node at the top, which has a left child, and that left child has two children of its own. To minimize the number of cameras needed, we can place one camera at the root node. This single camera will monitor the root itself, its left child, and both of its left child's children. Since all nodes are monitored with just one camera, the output for this example is 1. Now, consider the second example where the input tree is more unbalanced. The tree is represented as 0, 0, null, 0, null, 0, null, null, 0. Visually, this forms a chain of nodes leaning to the left, with no right children. To monitor all nodes in this tree, we need two cameras. One camera can be placed at the second node from the top, covering itself, its parent, and its immediate child. The other camera can be placed at the node at the bottom of the chain, ensuring all remaining nodes are covered. This strategic placement allows us to minimize the number of cameras, resulting in an output of 2. For the third example, we simplify things further. The input is just 0, meaning the tree contains only a single node, the root. In this case, we place one camera directly at the root to monitor it, and the output is 1. To wrap up, the constraints of the problem specify that the number of nodes in the tree can range from 1 to 10,000. The value of the node itself is irrelevant for solving the problem, and we're guaranteed that the data structure is a binary tree, meaning each node has at most two children. Some key edge cases include a single node tree, which will always require exactly one camera, and completely unbalanced trees, where nodes are arranged in a single chain. For larger, more complex trees with multiple branches, we'll need to carefully determine the optimal placement of cameras to minimize overlap and maximize coverage. The goal at every step is to ensure all nodes are monitored using the smallest number of cameras possible. To address the problem of placing the minimum number of cameras in a binary tree while ensuring that every node is monitored, we first consider two potential approaches. The first is the brute force approach, which involves trying all possible placements of cameras across the tree. The intuition here is straightforward: evaluate every subset of nodes to determine which configuration minimizes the number of cameras while ensuring all nodes are monitored. However, this method quickly becomes impractical as the tree size increases. The number of subsets grows exponentially, leading to a time complexity of 2 to the power of n, where n is the number of nodes. While brute force guarantees a correct solution, its exponential runtime makes it infeasible for larger trees. Additionally, the space complexity of n from the recursion stack further complicates its scalability. The key limitation here is that it doesn't take advantage of the tree structure to optimize the solution. Now, a second approach, the greedy method, attempts to address this inefficiency. The idea is to place cameras at nodes that provide local maximum coverage, meaning nodes where the camera can monitor the largest number of parent and child nodes. While this is faster and involves only a single traversal, it lacks the global perspective needed to guarantee the fewest cameras overall, as it focuses solely on local optimization. This makes the greedy approach unsuitable for this problem as well. The greedy approach, while simpler and faster, is limited by its inability to guarantee an optimal solution. It has a time complexity of n for a single traversal and a space complexity of h, where h is the height of the tree. However, its failure to account for global optimality leads us to consider a more robust strategy: dynamic programming on trees. This approach leverages the hierarchical structure of the tree and the problem's optimal substructure. By defining specific states for each node, we can systematically solve smaller subproblems and combine their solutions to achieve global optimality. Here's how we formalize this. For each node, we define three states. The first state, state 0, represents the minimum cameras needed if the node itself is monitored but does not have a camera. The second state, state 1, represents the minimum cameras needed if the node has a camera. Finally, state 2 represents the minimum cameras required to ensure the entire subtree rooted if this node is monitored. Using these states, we perform a post-order traversal of the tree, calculating the minimum number of cameras needed for each subtree by combining the results of its child nodes. The key insight here is that a node can be considered monitored if either it has a camera or its parent has one, allowing us to minimize redundancy in camera placement. Dynamic programming on trees proves to be the most efficient and effective approach for this problem. Its time complexity is O(n), as we only need a single post-order traversal to compute the states for all nodes. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. This method guarantees an optimal solution by systematically breaking the problem into smaller subproblems and combining their solutions. The trade-off, however, is the complexity involved in formulating the states and transitions. Despite this, the benefits far outweigh the challenges, making it the ideal choice. The brute force approach was dismissed due to its computational infeasibility, and the greedy method was rejected for its inability to ensure global optimality. Dynamic programming not only guarantees correctness but also scales efficiently for larger trees. The key to its success lies in defining the states state 0, state 1, and state 2 to represent different monitoring conditions. By carefully combining these states during the post-order traversal, we achieve a solution that is both optimal and efficient. While the implementation may require careful thought, the trade-off is justified by the accuracy and scalability of the solution, making it the clear choice for solving the binary tree cameras problem. In this problem, the goal is to determine the minimum number of cameras required to monitor all nodes in a binary tree. A node is considered monitored if it either has a camera placed on it or is directly connected to a node with a camera. To achieve the optimal solution, the problem can be broken down into three states for each node. State 0 indicates that the node is not covered, state 1 means the node is covered but does not have a camera in itself, and state 2 represents that the node has a camera. Using these states, we can systematically evaluate the tree to ensure that all nodes are monitored with the fewest cameras possible. The most efficient approach for this involves a post-order traversal using depth-first search, which ensures that decisions for a node are made only after assessing its children. This forms the backbone of our greedy algorithm, as we aim to place cameras only where absolutely necessary. A recursive function called DFS will be developed to handle these decisions at each node during the traversal. The DFS function is designed to return the state of the current node after evaluating its coverage. Specifically, it determines whether the node is covered without a camera, state 1, has a camera, state 2, or is not covered, state 0. To handle edge cases, when the function encounters a null node, such as a child of a leaf node, it is treated as covered, state 1, since no camera is required for null. At every non-null node, the function recursively evaluates its left and right children. Based on their states, the current node's state is determined. For example, if either child is not covered, state 0, the current node must have a camera, placing it in state 2. If either child already has a camera, state 2, the current node is covered without needing its own camera, placing it in state 1. Finally, if both children are covered without needing a camera, the current node remains uncovered, or state 0. This logic ensures that cameras are placed only where absolutely necessary. After completing the traversal, we must check the root node's state and place a camera there if it is still uncovered. To track the number of cameras placed during the traversal, a global variable camera_count is maintained in increment each time a node is assigned state 2. This approach relies heavily on the efficiency of post-order traversal, which ensures that each node evaluates its children's coverage states before making a decision about its own. The greedy nature of this algorithm guarantees that cameras are placed only when required, specifically when a child node is uncovered. Additionally, the state transitions for each node are designed to maintain consistency, ensuring that decisions at one node do not interfere with the coverage constraints of its parent or children. The algorithm uses core data structures such as a binary tree with left and right pointers, the global camera _count variable, and the implicit recursive stack generated by the DFS traversal. In terms of complexity, this approach is highly efficient with a time complexity of O(n), where n is the number of nodes, since each node is visited only once. The space complexity is O(h), where h is the height of the tree, due to the recursive calls in the stack. Consider the given example binary tree. Starting at the leaf nodes, their children are null and are therefore considered covered, state 1. Moving up, a camera is placed at the parent of these leaf nodes, marking it as state 2. This ensures that both the leaf nodes and their parent are now covered. The same logic is applied to the right subtree. Finally, at the root node, it is necessary to check if it is covered. If it remains uncovered, a camera is placed at the root to ensure full coverage of the tree. This example highlights the importance of post-order traversal, as it ensures that decisions about camera placement are made only after evaluating the states of all child nodes. To optimize further, null nodes are pruned early by immediately returning state 1, avoiding unnecessary computation. By carefully analyzing state transitions, the algorithm avoids redundant camera placements, achieving minimal coverage cost. This greedy DFS approach ensures that the tree is fully monitored with the least number of cameras while maintaining a low computational overhead. Here, we define a class called solution and implement the function minCameraCover, which calculates the minimum number of cameras needed to monitor all nodes in a binary tree. We start by defining 3 states to represent the condition of each node. Not _needed signifies that a node is already covered and does not require a camera. Has _camera indicates that a camera is placed at the node, while needs _coverage means the node needs to be covered by a camera. Next, we define a helper function called DFS, which performs a depth-first traversal of the tree. If the current node is null, it returns not _needed, as null nodes do not require coverage. For non-null nodes, we recursively check their left and right children. If either child is in the needs _coverage state, we place a camera at the current node, increment the camera count, and return has _camera for this node. Alternatively, if either child has a camera, the current node is already covered, so we return not _needed. Finally, if neither condition is met, the current node itself needs coverage, so we return needs _coverage. Now, we initialize a variable cameras to 0 to keep track of the total number of cameras placed. After defining the DFS function, we invoke it on the root of the tree. If the root is in the needs _coverage state after the traversal, it means we must add one more camera to ensure the root is covered. We then return the total camera count stored in self.cameras. This implementation efficiently calculates the minimum number of cameras required by leveraging post-order traversal and the 3 defined states, ensuring that each node and its children are optimally covered. Here, we start with the implementation of the solution in Java. We define 3 constant states to represent the coverage status of a node: not _needed for nodes that are already covered, has _camera for nodes where a camera is placed, and needs _coverage for nodes that require a camera. We also declare a variable, camera count, to keep track of the number of cameras used. The main method, minCameraCover, begins by checking if the root node needs coverage. If the root is determined to need coverage after the DFS traversal, we increment the camera count to ensure the root is covered. Finally, we return the total camera count. The helper method, DFS, recursively traverses the tree and determines the coverage status of each node. If the current node is null, it is considered not _needed since there's nothing to cover. Now, within the DFS method, we analyze the results of the left and right child nodes. If either the left or right child needs coverage, we place a camera at the current node, increment the camera count, and return has _camera to indicate that this node now has a camera. If either child already has a camera, the current node is covered, so we return not _needed. In cases where neither child has a camera and neither needs coverage, the current node itself is marked as needs _coverage, indicating it must be covered by its parent. Finally, we include the definition for the tree node class, which represents the structure of each node in the binary tree. Each tree node has a value, as well as references to its left and right child nodes. To solve this problem, let's start with a simple example. Here, we have a binary tree where the root node, labeled 0, has one child, also labeled 0. The goal is to determine where to place the cameras to ensure all nodes are covered. First, we start at the root node and call the DFS function, which recursively traverses the tree. Moving to the root's left child, we find that this node has no children, so recursive calls for its left and right children, both of which are none, return not underscore needed. Now, because this leaf node itself is not covered by any camera, it returns needs underscore coverage. At this point, we backtrack to the root node to evaluate its state based on its child's return value. The left child of the root returned needs underscore coverage, indicating it requires coverage. To address this, we place a camera at the left child node, incrementing the self.camera's counter to 1. By placing the camera here, this node is now covered and returns has underscore camera. At the final step, we check if the root node itself needs a camera. Since the root is already covered by the camera placed on its child, it does not require an additional camera. Therefore, the minimum number of cameras required for this tree is 1. Now, consider a balanced tree example. In this case, the root node has 2 children, and the left child further has 2 children of its own. We start at the root and traverse the left subtree. For the left child of the root, we process its 2 children, both of which are leaf nodes. These leaf nodes return needs underscore coverage, as they are not covered by any camera. To ensure coverage, we place a camera on their parent, the middle left node, and increment the self.camera's counter to 1. This node now returns has underscore camera, indicating it has a camera and covers its children. Next, we process the right child of the root, which is a leaf node and returns needs underscore coverage. Returning to the root, we find that the left subtree is covered because its child returned has underscore camera. However, the right child requires coverage, so we place another camera at the root, incrementing self.cameras to 2. In this tree, the minimum number of cameras needed is 2. Finally, let's look at a single node tree. Here, the tree consists of just the root node labeled 0. Since this node has no children, the recursive calls for its left and right children, both being none, return not underscore needed. However, the root node itself is not covered, so it returns needs underscore coverage. In the final step, we check if the root needs a camera. Since it does, we place a camera at the root and increment the self.camera's counter to 1. For this tree, the minimum number of cameras required is 1. The time complexity of this solution is O(n), where n is the number of nodes in the binary tree. This is because the algorithm uses a depth-first search, or DFS, which visits each node exactly once. For every node, a constant amount of work is performed. Specifically, the algorithm evaluates the states of the node's left and right children, and then determines its own state, which can be either needs underscore coverage, has underscore camera, or not underscore needed. Since these operations are all O(1), the total work done is directly proportional to the number of nodes. This holds true across all scenarios. Whether the tree is optimally configured, balanced, or highly skewed, the algorithm must traverse every node, making O(n) the time complexity in the best, average, and worst cases alike. Now, let's examine the space complexity, which is O(h), where h represents the height of the binary tree. The main contributor to space usage is the recursive call stack. Since the algorithm employs recursion to traverse the tree, the maximum depth of the recursion corresponds to the height of the tree. For a perfectly balanced binary tree, the height is log n, which means the space complexity is O log n. Conversely, in the worst-case scenario of a highly skewed tree, the height is equal to the number of nodes, n, resulting in O(n) space for the call stack. Additionally, the algorithm does not utilize any extra data structures beyond the recursion stack, so the auxiliary space usage is O(1). Therefore, the overall space complexity is dictated solely by the recursion depth, making it O(h). In terms of specific cases, the best-case scenario occurs with a perfectly balanced binary tree, where the recursion depth is log n, leading to O log n space complexity. The average case typically mirrors this, as most binary trees have a height proportional to log n. However, in the worst-case scenario of a completely skewed binary tree, the recursion depth equals the number of nodes, resulting in O(n) space complexity. Comparing this to a brute force approach highlights the efficiency of the optimized solution. A brute force method would involve generating all possible subsets of nodes, placing cameras, and verifying coverage. This approach requires exponential time, O(2 to the power of n), because there are 2 to the power of n possible subsets, and verifying coverage for each subset takes O(n) time. The total complexity of brute force is therefore O(n*2 to the power of n). In contrast, the current solution achieves O(n) time and O(h) space by leveraging states to minimize redundant computations and process each node exactly once. Finally, let's mathematically validate the big O analysis. For time complexity, let T(n) represent the time required to process a tree with n nodes. At each node, the algorithm processes its left and right subtrees, which have sizes L and R, respectively, and performs O(1) work at the current node. This gives us the recurrence relation T(n) equals T(L) plus T(R) plus O(1). Since the entire tree is traversed, the total work is proportional to the number of nodes, confirming the time complexity is O(n). For space complexity, let S(h) denote the space used by the recursion stack for a tree of height h. In the worst case of a skewed tree, h equals n, resulting in O(n) space. In the best case of a balanced tree, h equals log n, resulting in O log n space. Ultimately, the optimized solution achieves the best possible time complexity of O(n) and space complexity of O(h), making it both efficient and scalable compared to brute force methods. When solving the binary tree cameras problem, there are a few common mistakes to watch out for. First, incorrect base cases in recursive solutions can lead to runtime errors, especially if you forget to consider edge cases like single-node trees or null trees. For instance, in a tree with only one node, your solution must correctly handle placing a camera at the root. Next, redundant camera placements are another frequent issue. Placing cameras on every node without accounting for how subtrees are monitored can result in highly inefficient solutions. To avoid this, focus on minimizing the number of cameras by identifying strategic nodes that can cover multiple subtrees, leveraging dynamic programming or greedy approaches. Another critical mistake is failing to distinguish between nodes that are monitored by a camera versus nodes that have a camera themselves. This distinction is vital for minimizing the camera count. Finally, traversal order is important. Using the wrong order, such as pre-order instead of post-order, can lead to inaccurate results. Post-order traversal ensures that child nodes are processed first, which is essential for making informed decisions about their parent nodes afterward. Now, let's consider the inefficiency of brute force approaches. Trying all possible camera placements might seem like a straightforward way to solve the problem, but it's computationally expensive and impractical for larger trees. A better approach is to use dynamic programming or greedy strategies to intelligently narrow down the search space. One key insight for solving this problem involves breaking it into 3 distinct states: a node with a camera, a node that is monitored but does not have a camera, and a node that is not monitored. By using post-order traversal, you can make decisions about a node's children before deciding how to handle the parent, which aligns naturally with these state definitions. In interviews, you might be asked to explain how your solution minimizes the number of cameras. Be prepared to justify your approach, whether it's greedy or dynamic programming, and demonstrate its correctness. To further optimize your solution, memoization can be employed. This ensures that results for each node's states are stored, avoiding redundant calculations and improving efficiency. Additionally, interviewers often focus on time complexity, so it's important to explain why optimized solutions for this problem run in O(n). This efficiency is achieved because you only traverse the tree once, processing each node in constant time relative to its states. Beyond the binary tree cameras problem, there are related problems you may want to explore. For example, LeetCode 337, House Robber 3, is another dynamic programming problem on trees, while LeetCode 124, Binary Tree Maximum Path Sum, involves optimizing values along paths. Another interesting problem is LeetCode 250, Count Uni-Value Subtrees, which focuses on subtree properties, and of course, revisiting binary tree cameras itself is essential for mastery. These problems share some overlapping concepts, like tree traversal and state management, so understanding them can help strengthen your skills for solving tree-based challenges. Finally, let's compare different approaches to solving this problem and their trade-offs. Brute force is the simplest method conceptually, but its exponential time complexity makes it impractical for larger trees. It's mainly useful for very small trees or as a way to verify the correctness of other solutions. Dynamic programming combined with post-order traversal is the most efficient approach, with a time complexity of O(n). However, it requires careful handling of states and transitions, so it demands a deeper understanding of how to model the problem. On the other hand, the greedy approach is easier to implement and can work well for simpler variations of the problem. However, it may require additional logic to ensure correctness, especially in edge cases where greediness alone doesn't guarantee the optimal number of cameras. Choosing the right approach depends on the specific variation of the problem and the constraints you're working with. Great work! Today, we solved the binary tree cameras problem, focusing on optimal placement strategies using dynamic programming and greedy approaches. We covered time and space complexities while emphasizing key problem-solving concepts. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!